In microwave bands, generally they use a different nomenclature, starting from P to K. Okay. The last time I told you this is your set-top box, and if you look at FM, it is somewhere in the VHF region. Uh, Before the FM and all came up, it was HF and MF. That's what was available in the radio. So very long distance communication used to be HF. This was long distance communication. So what I mean by long distance is, suppose you want to receive BBC or Voice of America, it always used to be the HF band. But if you want to have the local reception, All India Radio, that used to be in the MF band. So All India Radio used to be the MF band. But nowadays even All India Radio operates on the FM band. I'm not sure whether they're still operating the MF band. In fact, all your mobiles, I think they are having only the FM band. So there's nothing like HF and MF. But in aviation, they use MF, HF, both MF and HF, and VHF and UHF. So typical MF application in aviation is what we saw last semester, NDBs, non-directional beacons. They operate on MF band. VHF is VOR, ILS, and all this stuff. Okay, they all operate in this VHF band. UHF is generally for what you call secret bands. Okay, for the military. So some secret frequencies are used in the UHF band. If you talk about GPS, that will be in L band. Okay, so across the spectrum, you will find applications, aviation-related applications. Now we will see a very basic derivation today about what sort of power levels you can expect. So let's assume that we are having a transmitter which is having an antenna. This is the transmitter side, and you have a receiver here. Distance being small d. So this is the receiver part. You have a transmitter here. This transmitting antenna, for the time being, you just take that it has a gain of GT. Gain is an increase, okay. Attenuation is a decrease. So it's a multiplying factor. As of now, if you say gain is 10, the power levels are getting multiplied by 10. Okay. So if at a distance, suppose this is an isotropic source, the power density at a distance d is nothing but Pt divided by 4 by d square. 4 by d square is the surface area of a sphere. So you can approximate the power density as Pt by 4 by d square. If you multiply that with the gain, so that becomes gain of the antenna, transmitting antenna, then you have this power density small p is equal to so much watts per meter square. So now it is watts by meter square. Sanjita, is it okay? I am trying to find out for a transmitted power Pt, what will be my received power at a distance d. Okay, that is our aim finally. Okay, now this is watts per meter square. Just look at the dimensions. You will be able to easily grab this. Nothing great about it. So this P times And let's assume this antenna has a area AR, receiving antenna has a antenna area of AR. So the power which will be intercepted by this antenna, because the radiation is going all over, and the amount of power which is being intercepted by this antenna is nothing but to multiply the small p by AR times. So watts in per meter squared into meter squared becomes watts. So this is what you are going to receive at a distance d. When we talk about, when we will subsequently we'll be discussing about antennas. There I'll tell you why this receiving antenna area is given by this formula, lambda squared into gain of that receiver by 4 pi. We'll either derive it or we'll just state it. So this area of the antenna is given by it. But you can just see the dimensions, okay? This is the dimensional is called P, 4 pi. So meter squared, meter squared. So you get that dimensions of the area. Now if you multiply, you add, this is 1, equation 1, and this is equation 2. So substituting this 2 in 1, you will get the actual power received in watts. Now you can, the advantage of having this in this form is it is now going to be frequency related because lambda is coming in. Okay. Earlier there was no frequency dependency. Now there is frequency dependency is there. Now what you have to do is just take log on both sides, multiply by 10. So this is squared, and if you invert it, it becomes minus. So this term becomes a minus because you are inverting it, 4 pi d by lambda. It's a much more easier way of representing the whole thing. So this 10 log to the power 10 times log to the base 10 into PR of PR is nothing but power received. So when you say 10 log to the base 10 of some power, this as this units called P in dB. So much, it's called decibels. 10 log 10 of any power is power in decibels. So what we essentially we are having is a PR here, received power is equal to, so this factor is nothing but power transmitted. These are all gains, okay? Gain of receiver antenna and gain of transmitting antenna. So here gain. Only thing which is negative is this term, the last term, which even by intuition you can say that more the distance, more is going to be the loss. Similarly, lambda, 1 by lambda is f. Okay, if you take it in terms of f, what happens is higher the frequency, higher will be the losses. So when I was asking why we should modulate, someone told that higher frequency means will reduce the loss. No, it's the other way around. Higher the frequency, more will be the loss. So if you know these parameters, antenna gains, because antenna gains are all fixed, okay, it's a fixed area for a given lambda. If you know this, what is the power in watts of the transmitter, then you will be able to estimate the received power at a distance d. So you people can just derive it now yourself. Sangeeta, can you follow the logic? How I am trying to get the received power?
Yes, sir.
Yeah, now kindly do it once yourself. Is it okay, Sangeeta? Okay.
Yes, sir,
So
it's okay. So just one doubt.
yeah,
The term PT by 4 pi d square, what is it signifying? The power transmitted divided by the
it's
area of
power
the
density
sphere.
at a distance d. Power density at a distance d. So
Then the
let's say
small p.
small d. Small d is the power density. You're asking about this one?
Yes, sir, the first equation.
Yeah, yeah.
P
PT
equal to
is
gain
the
times
yeah. PT
transmitted
is
power.
the yeah transmitted power. So power density at a distance d is PT by 4 pi d square. So let us
Okay.
say that it's a point source. Okay, transmitter is a point source, and it's radiating in isotropic pattern. Then the density, power density at a distance d is nothing but Pt by the surface area of the sphere, whose radius is d. Is it okay? No? So that's why you
Yes,
have
sir.
this units watts per meter square.
Meters.
Incidentally, now the other doubt you people will be having is how can an antenna have a gain? See, gain is unless you pump in some energy, how can you get more energy? You're giving some input energy, and antenna doesn't have any power supply, but still it gets you get a gain, right? So Raghavendra, any idea how you can how do you achieve this? Doesn't it's not logical, right? You seem to be getting more energy than what you have supplied to the system in the antenna. An antenna is a passive device. Okay, the answer is this gain is with respect to an isotropic antenna. So in a directional antenna, the energy is concentrated in one direction. Okay. So let us say this this is A and this is B. So gain is nothing but A by B in that direction. So it's not that energy comes out of nowhere. All you're doing is trying to concentrate that energy in a particular direction. So with respect to an isotropic source, you have a gain of so much. That's what it means. It is similar to your torchlight. Okay, you just keep the bulb inside the torch, whatever it is, just keep it outside and power it up. Light spreads all over the room, but the density at say on the wall, on the surface of the wall, is going to be something. Okay, x watts per x lumens per meter square. But the moment you concentrate it in one direction, then the lumens increases. So similarly, in EM waves also, the moment you concentrate the energy, then you get a gain. In the rider is in a particular direction. It's not that everywhere you get a gain. Okay. Now this is a very useful relationship. So now you can appreciate why the interplanetary mission antennas are so huge. Okay, the one at Bangalore and all for Mangalyaan and all, they are such massive structures. Similarly, when you go for radio astronomy, where you are trying to listen to some causes, EM waves, then again it's all so many light years away, and losses are going to be really high. So the only way you can get something useful is increase the antenna gain, and this antenna gain is directly a function of its area. So larger the area, better is the gain. Okay. Now we know what is the received power. When we talk about receivers, two important characteristics are to be kept in mind. Can someone recollect what it is? Any electronic communication receiver?
Selectivity and sensitivity.
Yeah, good, very good. So selectivity and sensitivity. Selectivity is you must be able to select that particular frequency, right? Out of because the spectrum is very large, and within that you will have to select that particular frequency. That's why you are using these local oscillators to do that job. Sensitivity is the minimum signal which you can receive, which is nothing but the relationship what we have derived now, PR. If your sensitivity is more than this, then you are not going to receive this signal. Okay, so in that sense, if you want a very highly sensitive receiver, it should be able to sense something which is less than the PR. So these two parameters are important, and we have a relationship for PR now. So it's applicable for all electronic communication receivers. Okay. In fact, the selectivity part is also comes in this stage. There will be some filters which will ensure that you don't select some unwanted frequencies. And this filter can also come here also. At this stage also you can have a filter. Different stages you have a filter, and then try to select the will be again depend on this antenna gain, then your RF amplifiers and all this stuff. Now coming back to EMA propagations, once you launch a radiator signal, it just propagates through space. And what you have seen in the relationship is the energy level is going to decrease with distance. Not only because of distance, it also gets affected by a lot of things. It's not that it's just a free space and you're receiving everything. Okay. Now, in between, there will be some buildings, some vegetation, and a lot of things. Okay. So, it's not that simple that this, whatever you are receiving PR is going to be an ideal situation. It's going to be much less than that. One is radio frequencies are going to be like light, so they travel in straight lines. Uh, then power is 1 by d squared in vacuum. But then the problem is it gets affected by all this shadowing, like within your house, you lose your mobile signals. Okay, that's because there is some shadowing effect. They get reflected, refracted, then you have the scattering phenomena, and then diffraction, which is nothing but bending of the waves. So, like light, radio waves also have all these things. And in spite of that, you receive your mobile signals in the house. Okay. So, that's the technology. Another major problem is something called as multi-path propagation. So, you are sending a pulse, say this blue one, after some time you are sending a red one. Okay. So let us say your receiver is here. One is this direct path. Okay, this is the ideal path. But it might so happen that the same signal gets reflected from some other structure. So in time, if you see, you will get this blue pulse coming after the red pulse. So this multipath signals also create a hell of a lot of problems. Again, I'll repeat it. Let's assume that it's not a blue color or red color, just for explanation's sake. There is a blue pulse and a red pulse. If the communication is ideal, it would be from this transmitter to this receiver. That's a staying line. But it might so happen that it can also get reflected. So which means there is a time lag. And once you have this time lag, these two pulses can overlap and create a lot of errors. Uh, so this happens like if you are having a radar and there is a mountain or some structure here, uh, you can always have this multipath reflections coming and interfering with the on the radar screen. So multipath problems is quite severe. Okay, there are some ways to address this issue also. So this in general is about EM wave propagation. When we talk about modes of propagation, I am just going back to your 12th standard physics book, last chapter. There are three ways by which this propagation can take place. One is this direct method. Okay, so let's assume that there is no reflected thing. Direct communication, it's called line of sight communication, or it's also called space waves. The other method is if you can launch the wave pointing towards the sky, then because of change in refractive index, this refractive index can change due to ionization at some that we'll see in detail what it is. It can actually start bending, start reflecting like this. So because it's getting reflected from this sky, it is called sky wave. The other one is called, first one is called space wave. So the advantage is you can have very long distances. Uh, Sandita, why this distance there will be a restriction in the space wave?
Because of the curvature of the Earth.
Yeah, because of the curvature of the Earth. Okay, good. So if you have a antenna here and you are transmitting, definitely this. If you are going to have a receiver here, you are not able. You will not be able to receive it. Okay. So there is a LOS is having that restriction. Skyway, on the other hand, doesn't have that problem. Okay, you can even go up to 9,000 kilometers easily. Uh, so if you say Earth's circumference is around 40,000 kilometers, so at least 25% of the circumference you can really cover. Not only that, it's also possible that you can have multi-hop transmission. Like this is the Earth surface, and let's say the ionosphere is one fictitious sphere. You can have this sort of transmissions coming up. So around the globe also you can get it. That's why at times even Voice of America transmitted from Boston, you can receive it in Chennai. That is because of this multipath, multi-hop propagation. It's not multipath, multi-hop. And the last method is something called as ground wave. In ground wave, what you do is you have a vertical antenna. Okay. We'll see all these three things in detail in the next class. This wave propagates as if the ground is a perfect conductor. It starts jumping from the transmitter and starts propagating along the surface of the earth. So it's called ground wave or surface wave. And this is what is happening in the MF band. So NDBs and all, they work on this, and definitely the range is much better than the line of sight. Transoceanic flights, there is no way you can have line of sight. So all HF communication for aircrafts whenever they fly over the oceans is on HF band. So voice communication for aircrafts over oceans, flying over oceans is still HF, though they are coming up with some satellite-based systems. And LOS is ATC to aircraft. So that's around generally around 100 kilometers. So 100 kilometers, 9,000 kilometers, and MF maybe 1,000 kilometers. Just to give you some idea about the ranges. Okay, for the class, what do you think will be the disadvantage of uh, MF? Anyone can answer. Sandhita told that LOS has a disadvantage because of curvature of Earth. Fine. Similarly, what do you think is the disadvantage of MF band?
So it'll have much more disturbances which will cause errors because we can expect much more activity in the ground than we can expect in the air.
It's not a very reliable, I agree with you, because you assume that this is a perfect conductor. Anyway, it's not a perfect conductor. Earth is not, surface is not that's not a disturbance, it will lead to more attenuation actually. Reduction in strength. That we'll see in next class. Anything else? This is MF, HF, and okay, I'll just give you a clue. This is VHF. Let us say, I'll give some number, 300 megahertz, and this, let us say, maximum is 30 megahertz, and this is 300 kilohertz. So if you see what is lambda for the first one, it is 300 megahertz, right? 300 into, uh, sorry, 3 into 10 power 8 by, how much is this? 3 into 10 power 6. 300, right? So it becomes 100 means 8. So it's up, it is 1 meter. Now if you say 30 megahertz, it becomes 10 meters. Okay. And if it is 300 kilohertz, it's 3 into 10 power 6, right? 10 power, so lambda is 3 into 10 power 8 by 3 into kilohertz, right? 300 into 10 power 3, 10 power 5. So it is 1 kilometer. So what's going to happen now? What is it going to really affect? Because the lambda is very large in MF.
Huge antennas, sir.
Yeah, antenna size is going to be really large, right? Because it's lambda by 10. So at least you require a 100 meter antenna. 100 meter is just 300 feet, okay? 300 means 10 feet for each store, each floor. Approximately, you're talking about a 30-story building. Whereas if you look at VHF, it is 1 meter, 1/10 of a meter, which is very small as the size of your pen. Okay, so you can imagine the scale. You require really huge antennas. Okay, now an interesting question for you guys. If okay, transmitter side, I can always have a very tall antenna, which is let us say 100 meters in height. But how about the receiver? People were using MF band. Your father and grandfathers, they are all listening to radios. They are all operating on MF band. How did they manage to receive it without having such a long wire? Are you getting my point, Yuval?
Yes, sir.
See, MF band was there earlier, right from Marconi days, it is there. Uh, and we had very small radios, portable radios, which can fit into our pockets. How was it possible? But physics is physics. You require 1 kilometer antenna. Worst case 100-meter antenna.
I don't know, sir.
No, no, just think about, think, it's open to the class. No? Okay. Anyone can make a guess. It is only geometry, okay? Something to do with geometry.
Sir, you can adjust the antenna in any direction, sir.
No, direction, it's just a wire, okay? Because you don't know which direction the transmitter is coming, transmission is coming from. So both are wires. Transmitter also is a wire, and this one also is a wire. Yeah, you can have some directivity, no issues. I think you are talking in terms of the equation what we were discussing earlier, that Ferris. But again, there is the issue. No? If you want to have some directivity, then you should require an antenna which is spherical or a dish-like structure. So where is the question of putting a dish inside your pocket?
So there were pull-apart antennas, like they could reduce the size and increase it
But
by.
how, whatever it is, it's called a telescopic antenna. Length is maximum. Okay, maximum you can have is around 10 feet. And this pocket radios, if I recollect, it's only 2 feet or 3 feet. That's all. Yeah, it's a good observation, telescopic antenna. I think, where have you seen those antennas?
My grandfather used to have.
Okay, okay. Because nowadays,
Saturdays.
even in the cars, you don't get those antennas.
Yeah, I think it's there in some cars actually, outside.
Nowadays, it's not there. Oh, okay. Now I'll give you a clue. If you had observed the antenna on a car,
Mhm.
okay, then you
Yeah.
can tell me how it's going to work. Every car has an antenna nowadays, okay? Either it's flush mounted or one small stick projecting out. But if you look at it very closely, you will get some clue.
There's a small spherical part of the.
But I have to satisfy this condition of length. Where am I going to get? So the restriction is I want to put this 100 meters wire inside my pocket. Or even if you say this FM, which is uh, those 30 megahertz, it can go up to 90 megahertz. That's what you people are receiving. So one third, maybe still you're having a problem. How do you make very small antennas? Because your mobile is having an antenna. It receives FM, but I don't see any antenna at all on a mobile.
So does it get reflected from each device, sir?
No, reflected means more loss. And let's even assume that there's an ideal situation that there is one MF transmitter and you are the only person having one receiver and it's free space. No reflection, no obstructions, nothing. Sanita, you understood the problem, no?
Yes, sir.
Yeah. Okay, fine. So with that, I'll end the class today, and I'll leave it to the class to figure out how you can uh, overcome this problem to fit a large antenna in a small space. Okay. Okay. Thanks, Sanjita. Huh? We'll meet in the next class. That'll be next week, right? Okay. Bye.